Finding an exoplanet is largely a problem of contrast. The objects we want to study are cold, low in mass, and separated from us by thousands of light-years of empty space. The most prolific detection methods we use, transit photometry and radio velocity, rely on measuring a star's light dipping or its position wobbling. Consequently, those methods are highly biased toward finding massive planets orbiting extremely close to their host stars. This chart graphs our exoplanet census along planetary mass and orbital separation. The resulting clusters leave massive gaps. That gap is where gravitational microlensing operates, targeting a completely separate population of planets well outside the tight orbital ranges of other techniques. Because it does not rely on the light emitted by the planet or its host star, microlensing provides our only reliable method for detecting cold, low-mass worlds, and even free-floating rogue planets drifting entirely on their own. The mechanism relies on a chance alignment. When a foreground star passes precisely between Earth and a distant background star, the foreground star's gravity bends and amplifies the background light. This plot captures data from event OGLE 2005 BLG 390. Over several weeks, the background star's brightness symmetrically peaks and falls. However, superimposed on the right side is a secondary spike. That brief deviation indicates the presence of a planet. Translating a slight fluctuation in light into the exact mass and orbit of a planet 22,000 light-years away requires extracting structural data from the shape of the spike itself. These anomalies in the light curve are not random noise. They are one-dimensional cross-sections of a two-dimensional boundary of infinite magnification, known as a caustic. To read the data contained in that spike, we have to model exactly how mass deforms the geometry of spacetime into these distinct optical traps. This diagram illustrates the lens equation, mapping the geometric relationship between the observer, the lens, and the source star. The total angular scale is dictated by the distances between the planes, observer to lens, observer to source, and lens to source. Because the lens's mass curves spacetime, light rays traveling from the source follow null geodesics. They bend around the massive object, arriving at the observer from multiple angles to create two distinct shifted images. While our optical telescopes cannot resolve these separate images, their combined solid angle is larger than the unlensed source. We observe this increase in apparent size as a dramatic magnification in brightness. To calculate this magnification across an entire area of space, astronomers use inverse ray shooting, tracing simulated photons from the observer backward through the gravitational curvature and mapping where they land on the source plane. The result is a magnification map, a two-dimensional density distribution of deflected rays. The higher the concentration of rays in a given pixel, the higher the magnification. The specific locations in this mapping where the lens equation becomes singular, where magnification mathematically diverges to infinity, are the caustics. For a single isolated star acting as a point mass, the caustic is degenerated to a single point. If the alignment is perfect, it produces a symmetrical annulus of light known as an Einstein ring. That symmetry shatters the moment we introduce a second mass, an exoplanet, into the lens plane. The resulting geometry is entirely defined by two variables, the mass ratio between the star and the planet, and their projected orbital separation. This image displays the complex two-body magnification pattern. The gravity of the planet fractures the singular point caustic into a set of closed, asymmetric curves. This diagram isolates the anatomy of that planetary caustic. It consists of sharp connecting points called cusps, bound by sweeping lines called folds. As a strict rule of optical geometry, the magnification inside these closed boundaries is always significantly higher than the magnification outside. The fold itself has zero width. It represents the exact threshold in space where the lens equation returns a singularity.
Introducing a planet creates a dense, treacherous optical landscape. Even microscopic shifts in a background star's position relative to these folds will trigger massive, sudden changes in observable brightness. The one-dimensional light curve we measure from Earth is simply a timeline of a background star moving in a straight line across this two-dimensional map. As the source star's trajectory intersects the caustic geometry, its brightness spikes precisely as it crosses the fold. This graph compares two distinct light curves. The exact angle at which the source star impacts the caustic dictates the unique topology and amplitude of the spike we record. The most intense variations occur during resonant lensing, which happens when a planet's projected separation is near 1 Einstein radius from its host star. These panels map the highly sensitive shifting magnification patterns produced by a Saturn mass planet inside this resonant zone. The black arrows represent 3 different star trajectories, and these plots show the resulting difference light curves. Each distinct trajectory across the caustic yields a totally unique profile of peaks and dips over time. By analyzing the spacing and amplitude of these peaks, researchers can solve the lens equation in reverse, isolating the planet's exact mass ratio and orbital separation. We never actually see the planet itself. We are measuring the kinematic scars its mass leaves on the fabric of spacetime. This graphic diagrams systems with up to 8 exoplanets positioned inside and outside the host star's Einstein radius, creating deeply complex overlapping caustic fields. Because the light curve is a deterministic geometric signature, it allows us to reliably reverse engineer the architecture of entirely dark planetary systems. Microlensing events are strictly transient. They happen once, and because the stars are in constant motion, the alignment never repeats, leaving astronomers without a way to double-check their initial data. The only solution is patience. Researchers must wait years for the foreground lens star and the background source star to drift physically far enough apart in the sky to be observed independently. To verify the mass of a planet discovered in 2003, researchers utilized the Hubble Space Telescope to execute a follow-up observation of the host star. Even after 2 years of drift, the offset between the two stars was only 0.7 milliarcseconds. The angular width of a dime seen from 3,000 miles away varied in a dense galactic star field. By utilizing multiple colored filters, Hubble successfully recorded a color offset in the overlapping light, distinguishing the red foreground host from the background star behind it. Confirming the exact mass and distance of the host star anchors the variables in the lens equation, allowing researchers to lock in a highly precise mass for the orbiting planet. High-precision astrometry bridges the gap, proving that our mathematical magnification maps accurately reflect physical multi-body systems. The next frontier in microlensing involves adding a third mass to the lens plane, detecting exomoons. Expanding the geometry to a triple lens system drastically increases the mathematical complexity, requiring the solution of a 10th-order polynomial equation. This simulation images the nested caustic structure of a star, an exoplanet, and an exomoon. The moon generates its own microscopic caustic folded deep within the planet's larger magnification pattern. Detecting the anomaly produced by that exomoon requires immense observational discipline, demanding visual photometric precision down to 20 millimagnitudes, with sampling rates of 1 frame every 15 minutes. Tracking these miniature fluctuations pushes our instruments to their absolute limits, serving as the ultimate test of our ability to decode space-time geometry. Microlensing takes the central limitation of astronomy, the immense distances and overwhelming darkness of space, and weaponizes it into an optical tool of extreme precision. By understanding the architecture of general relativity, we are mapping the smallest, coldest, and most elusive objects in the galaxy, one light curve at a time.